Assalamualaikum and good morning everyone. Today we present our work on star-shaped trinuclear organometallic complexes featuring a unique benzo 1,2B, 3,4B prime, 5,6B double prime, trithiophenol triethynyl backbone. These complexes are synthesized to explore their electrochemical properties and application in material science. Under the guidance of Associate Professor Dr. Muhammad Sukru Muhammad Yusof, our team, Hajar, Balkis and Ain, aims to bridge the experimental synthesis with theoretical insight. So let's begin our presentation.
So this is for our introduction. So which is our first compound. So the IUPAC name for our first compound is 3-cyclopentadienyl bis-diphenyl phosphine ruthenium. So next is for our 18 valence electron count. So for Ru, ruthenium is equal to 8 electron. So 5 cyclopentadienyl equal to 5 electron. 2 diphenylphosphine is 2 multiplied by 2 electron equal to 4 electron. So total is 17 electron. So for our second compound is 3-cyclopentadienyl bis-diphenyl phosphine ion. Same like the first one, the first compound. So for the 18 valence electron count, so for iron equal to 8 electron. Cyclopentadienyl is 5 electron. So 2 diphenylphosphine is equal to 2 multiplied by 2 electron equal to 4 electron. So total same like the first compound is 17 electron.
Now, let's take a look at the synthesis part. First, we synthesize intermediate 3E by reacting benzo-trithiophenol with N-bromosuccinimide in a mix of dichloromethane and acetic acid. After 90 hours of stirring, we isolated a light purple solid with a 65% yield. Next, intermediate 3E was transformed into 3F using trimethylsilyacetylene and a palladium catalyst. Refluxing for 20 hours gave a white solid in 40% yield after purification. Let's continue to the synthesis part. With 3F ready, we synthesize a triruthenium complex by reacting it with a ruthenium precursor and potassium fluoride. After 48 hours of reflux, a yellow powder was obtained in 54% yield. Finally, a treated complex was prepared using a similar approach. Sequential addition of reagents in methanol over 40 hours yielded a red-brown powder at 30%.
Assalamualaikum warahmatullahi wabarakatuh. My name is Balkis binti Nazir at 67609. Today I will discuss about the star-shaped trinuclear complexes featuring a benzo trithiophenol triethynyl, BTT triethynyl, backbone coordinated to DPPE, capped ruthenium or ion centers. This architecture showcases how ligand design tunes electronic communication for molecular electronic. The synthesis hinges on 3 steps. The first one is functionalizing the BTT core with TMS ethynyl groups by Sonogashira coupling. The second one is distillation to expose terminal alkyne, and the last one is coordination to MCP DPPE fragments. The CP and DPPE ligands ensure the stability and control geometry. We begin by bromination of BTT core using NBS. This is the bromination of BTT 3D to 3E. That is insults. Handles by attaching TMS ethynyl group letter. The electron-rich thiophene rings direct bromination to the 258 positions, preserving the symmetry for trinuclear assembly. Next is Sonogashira coupling 3E to 3F. Next, PD catalyzed Sonogashira coupling graft TMS ethynyl arms onto the brominated BTT. The TMS group act as placeholders, preventing unwanted polymerization. After reflux, we obtain the key intermediate TMS ethynyl BTT, which is 3F from the diagram. Next is desilylation 3F to terminal alkyne. With TMS ethynyl BTT, which is 3F, in hand, we remove the TMS groups to liberate reactive terminal alkynes. For ruthenium, KF cleanly cleaves TMS. For iron, milder K2CO3 or KOTBU avoids degrading the sensitive, which is FeCP DPPE center. Okay, the last one is metal complexation. The terminal alkyne now bind to MCP-DPPE. The CP-DPPE ligands enforce to pseudo-octahedral geometry while BTT triadenyl bridge mediates electronic coupling. X-ray structures confirm the steric demands of CP cause slightly distortions.
So the application for our journal is molecular electronic, suitable for a single molecule transistor and logic gates due to rigid pi-conjugated frameworks and tunable redox behavior. Second is optoelectronic devices, useful in organic light-emitting diodes or OLED due to efficient charge transfer MLCT (metal to ligand) and ILCT (intra-ligand charge transfer) abilities. So the third one is photovoltaics, applicable in perovskite solar cell as effective cold transporting material. Uh, the fourth application is redox-based devices. Reversible multi-electron redox processes allow use in molecular switches and data storage devices. So the next application is chemical sensor. Spectro-electrochemical responsiveness enable sensor development. So the last application is molecular spintronics. Weak but controllable spin coupling between metal center shows potential in spintronic application.
So that's all from us. Thank you.